Hello, welcome to our afternoon session in Track 1 at the BRL conference. We are starting off this afternoon with Nathan Lepora from the bio-robotic touch section we've got at the BRL. And I think I'll just let you go ahead if you're ready, Nathan.
Okay, cool. Thank you. So I'm Nathan Lepora. I'm Professor of Robotics and AI at the University of Bristol and Bristol Robotics Laboratory. So I lead the tactile robotics group, which is about 15 people or so, maybe a bit bigger. So I'm going to talk with you today about future robot dexterity. Okay, so why would we want robot dexterity? I mean, this should kind of be obvious of why we would want robots with the dexterity of humans, because then the robots can automate the jobs that many of the jobs that we would like humans not to do but currently have to do, so dangerous, dull, etc. jobs. So they could be automated by robots if they had comparable dexterity to humans, which obviously they don't currently have, because humans are still doing some of these quite difficult jobs. So that's why we need robot dexterity. It's been, as I would see it from my lens, it's kind of been the vision of the fields since its inception, maybe 100 years ago or so. And also it's always kind of been an elusive problem, but this does seem to be a problem which is getting tackled at the moment, and there's been quite rapid progress being made in the last 10 years or so, worldwide. And I'm going to discuss contributions that my group has been making in this area. So the applications that once you get robots that can handle objects, the environment, interact with the environment with the agility and dexterity of humans, then suddenly a load of quite societally important applications become available, from say automated logistics, distributing goods to customers automatically. A lot of that's still packaged by hand. Obviously advances in industrial automation, agriculture, that's still a very human, laborious industry, particularly fruit picking and vegetable harvesting. Haptics and VR is another application. Teleoperating robots, having a robot avatar. There's many applications of that technology. For example, in like hazardous nuclear environments and so on. Healthcare robotics, education. This is an engaging way to teach children about STEM through interactive robotics. All kids love robots, so why not use it to inspire and educate them? And then other tasks like chores around the home, domestic chores, etc. So I think that's why robot dexterity. So how is robotics doing? So as I was saying earlier, there has been a rapid increase in the capabilities of robot dexterity over the last decade. Whereas, say, in the previous decades, the kind of state of the art was these kind of rigid, say, three-fingered, some anthropomorphic hands, but kind of, very robotic, if you like, sort of motors and rigid links. And then there was quite a major shift that happened between 5 and 10 years ago in the movement to more kind of compliant structures in the robot hands, which maybe we would see now as soft hands, but basically taking advantage of the compliance and the under-actuation of the robot hands in order to have more robustness in their interaction with the surroundings. So there was the IHY hand, so that's famous because it won the DARPA Grand Challenge in autonomous manipulation about 8 years ago. It was open sourced and also commercialized by Right Hand Robotics. And that I would say has given quite a step change in the field. And then a little bit later, there was the advances in soft hands that are based on similar principles, under-actuatedness and softness for the interaction, but now being more inspired by the form and function of the human hand. And then I guess everybody's seen the demonstrations of that OpenAI have done with the shadow dexterous hand, where it's a move in hand blocks and quite complicated dexterity. So now that was done with a fully actuated hand, not a soft hand, but really taking advantage of advanced AI techniques, deep reinforcement learning, and computer vision they used to solve that. So all of these hands I've discussed here and applications of them are missing a sense of touch, and I would see that as the kind of missing ingredient that is needed to kind of close that gap between the function of these quite sophisticated robot hands and the dexterity of the human hand. So the human hand has been honed by millions of years of evolution into a general purpose manipulation device. Nothing else comes close. People talk about how fantastic, say, crows are at tool use, or octopuses at unscrewing lids. We're kind of surprised by that, because that is a kind of something we can do, and we think that has been intelligent. But actually, it's completely pales into kind of insignificance, the kind of things we can do with our hands, when you consider that all technology has basically stemmed from the use of our hands. I mean, you don't get animals building skyscrapers and digital computers, and to a large part, that has been enabled by our capabilities with our hands to develop technology. So surely we should look to the human hand to design and deploy robots that are capable of human-like dexterity. And a necessary aspect of human hand function is our sense of touch. Our hands don't work properly if they don't have a sense of touch. So how do you do robot touch? If this, this is the kind of the question I asked myself several years ago when starting the lab. What do you need to do to get like advanced robot touch that's similar to human touch? Well, it's a challenge because of the number of different disciplines that are needed to kind of address this problem of how to do robot touch. So you need to go from soft robotics, as I was discussing earlier, to advanced AI. That for sure is going to be critical in the control and use of the hands. Unfortunately, we've had a revolution recently in AI over the last 5-10 years. So that's surely part of the puzzle. Neurophysiology, if you want to have robot touch that's like human touch, you have to understand how this human sense of touch works. Neuroscience, it would be a good thing to understand how our brains are able to control our hands and do dexterity. That would be useful information. And then you obviously need this hardware isn't available to buy, so you need to make it yourself in the lab. So you need to know about how to build and design robot hardware. And you also need to know about how to do robot control, which there's a strong there's 50 years of expertise in robot control that you should look to as well for controlling these hands. So it's a challenge because of the interdisciplinarity that's required to tackle this question. So coming to the work in my lab, so we would see our places. I would see our places fitting in to the field as soft biometric optical tactile sensing. So I'll explain what that means. So the hardware that we use in my lab is called the BRL tactip, tactile fingertip. It was invented before my time at Bristol. Jonathan Rossiter led that research. He's now obviously a well-known figure in Bristol, in soft robotics internationally. So he led that work with Craig Chorley and developed the original design of the tactip about 12 years ago now. And then I'll discuss what my lab has been doing with it since. But the idea for the tactip is it was inspired by the structures within human skin that I'll come to, that basically act as a kind of magnifier of the contact on the skin. And then there's a camera inside it, which I'll come to why that's a good thing in a minute. So it's a form of tactile sensor called an optical tactile sensor. So I kind of refer to this as a soft bot because it's a soft sensor, it's biometric, it's optical, it uses a camera, and it's a tactile sensor. So I see that as a soft bot. Now, soft biometric optical tactile sensing, as I said, the key things are there's a biometric transduction mechanism, whereas the structure of the 3D printed structure of the tactile skin mimics the structure between the top two layers of human skin, the dermis and epidermis, in that there's this kind of, in human skin, there's this 3D structure where the outer stiffer layer of skin, the epidermis, protrudes into the softer layers of skin underneath, the dermis, with these dermal papillae, and they act as levers in our skin, which amplifies the contact at the surface to the mechanoreceptors, which are distributed around these papillae, and basically turn that contact into nerve signals. So that same structure, so Jonathan and Craig Chorley, you know, they mimicked that structure originally in the tactile, and then, you know, say my lab now uses that same design principle to build our own skin through 3D printing. And there's a very similar structure, that you have these biometric papillae protruding from the outer layer of skin into the sensor. There's markers on the tips of those, and the movement of those markers, which is amplified because of these levers, is picked up by a camera. Now, because my lab uses 3D printing to build this tactile skin, to build these tactile sensors, it's meant that it's become a more straightforward task to customize the designs and the integration of these sensors. So we've kind of proliferated the kind of shapes and sizes of them, as you can see in this picture here, from tactile feet, which Lizzie is going to be talking about, and to longer sensors, smaller sensors, fatter sensors, sensors with whiskers on them. And then the key development as well has been to integrate and miniaturize those tactile sensors into robotic hands. And I'll describe some of the progress on there, but basically that was done with Ben Ward-Cherriot originally, and that kind of, there's been a progression from kind of one movable finger to two to three to something that now looks a lot like the human hand in form and function. Okay, so how does it work? So say it's biometric. One print in the skin, there are two types of mechanoreceptor, which, if you like, turn skin deformation into nerve signals. One of those is called slowly adapting, and we represent as movement of the markers, and they basically give geometric information about the contact. And kind of strangely, what they pick up is not pressure, not indentational in the skin. They pick up shear in the skin because of these sideways movements of the markers. Now, a human skin is known to work in that same way. It's quite counterintuitive. We don't feel pressure directly. We actually feel shear directly at the surface of our skin. But say that is mimicked in this design of the sensor. And then the other type of signal that comes from the skin, but which we mimic in the tactile sensor, is called rapidly adapting sensors. So we use a measure of marker speed for that, and it turns out that signal is really well suited for detecting changes in contact, such as slippage. Now, slip is a really important thing to have as a capability of our hands, because obviously the function of our hand is to pick up objects and carry on holding them. So it's important to know if we're about to drop them as we're manipulating or holding them. And so we have a sophisticated sense of slip detection in the skin. Now, it turns out that this design of the tactile, although it was designed for different reasons, the biomimicry and edge detection, turns out it gets this slip detection capability right. So this sensor's a very effective slip detector. And we've had a stream of work with Jasper James, who's worked this through in depth. Okay, and then there's other biometric functions that can be brought into the sensor that I won't go into here, but we kind of, as a lab, we've been looking into what are the other functions that human skin does, the other properties that it has, and how can this be brought into the design of the tactile sensor to give it the capabilities of human sensor touch, which we think are important for dexterity. Okay, so the rest of my talk is going to be on some demonstrations of what we can do with the sensor. These are mainly going to be video demonstrations, so nice and easy to follow, and they illustrate where it's illustrations for robot dexterity, and also illustrate where AI has taken the field. So all of these demos were done fairly recently in my lab in the last year or two. All of them relied on using AI techniques such as deep learning, and that was really the enabling step, I would say, to getting some of these capabilities that you're about to see. So I say these were all done recently. The papers are at the bottom of the slides. If you notice, they're all 2020, 2021. Just want to emphasize that. And that emphasizes how quickly this field is moving, because obviously we're one group and there's many, this is a large field in robotics that is advancing quite rapidly. Okay, so firstly on to tactile grasping. So this was the hand that Jasper built, the tactile Model O. So this is the hand I mentioned earlier that won the DARPA Grand Challenge, and then they open sourced the designs. So we built those open source designs in our lab and integrated them with the tactip. So we call this the tactile Model O. So the designs here. So I'll show you what kind of things we do with that. So, or Jasper does with that. So this is an example of a hand. So the hand is very good at picking up objects. There's a few wires and stuff here. We've been working on improving the prettiness of it. But so the hand is very good at picking up objects because that's why it won the DARPA Grand Challenge. And what the tactile sensing here does is it enables, firstly, to recognize what the item is, which is a useful capability. So that, for example, this case, it will successfully recognize it's a strawberry. But another useful capability that it has is to predict whether, when lifting that item, whether it's going to be a successful lift or not. So that's a useful thing. You want to know if your grasp is secure before you use that grasp. So this Rubik's Cube, it predicted it and said it was going to pick it up fine. Happens to pick this up again in a slightly different way. And then this is going to be a failure case. But as you see, it predicts it was going to fail. So this is a useful thing to know, for example, in logistics, if you were, packing items into crates and so on. But it shows the capabilities of what you can do with touch, because this is not possible to do without a sense of touch on the hand. Here's an example of slip detection. So I was saying earlier, the hand is quite the tactile sensor is an effective detector of slip. So what it's doing is what's called detecting global slip here. So it's relaxing the grip until the item begins to fall, and then it detects it and manages to recatch it before the item slips from the grasp. So this is actually quite hard because you have to react quite quick. The robot has to react very quickly and reliably to recatch an object as it's literally falling from the grasp. So Jasper works hard on this to get the late, and sometimes it fails, but 95% of the time it works. And as you see, it's demonstrating that the hand can detect slip and correct for it because of this sense of touch. Okay, so I'll move on to some other applications now. So we're going to do tactile servo control. So this is a combination of deep learning for tactile perception with feedback control based on visual servoing. Details aren't so important, but just to kind of say it's kind of analogous to a PID control loop, but integrated with deep learning methods for processing the tactile data. So this is the kind of thing you can do with that. So you can now feel and explore over quite complex 3D shapes, just using a sensor touch with a fairly basic controller, but fairly sophisticated perception system. There's a lot of generalization happening here. It was trained on something that didn't look at all like this porcelain bust. It was a kind of a flat plane it was trained on, but then it generalized well to this bust, and basically it just works. It feels over the shape, and it doesn't break itself or the shape. And then the same algorithm, nothing's changed. It's just exactly the same algorithm, because it has this kind of generality, can then work in feeling around basically all the kind of complex shapes we had kicking around to try it out. So this is kind of a direct analogy of, you imagine you were feeling over your face or something, or you're feeling your hair. This is something we perform subconsciously in humans all the time, but it's actually quite a challenging task to set up in robotics, and we managed to crack it, I say, by using modern advances in AI, basically, to get to these capabilities. Okay, so non-prehensile manipulation. So this is manipulation not using hands, but using single fingers. It's also based on this tactile servo control, but John Lloyd, who did this work, has had he's a better control engineer than I am, and he has this quite sophisticated control loop. But it's basically a version of servo control, like I was showing earlier. So now, just using a sense of touch and knowing a bit of information about where the end effector is and where you want to push the item to, it's just using a sense of touch. It's now able to do this to push these objects to a desired goal location. So to successfully push them in kind of adversarial conditions where you kind of set it off in the wrong direction and so on. So it works very robustly. And kind of, and then we threw again some objects at it to kind of show that it is generality. I mean, the key thing here is we see this as a kind of precursor to in-hand manipulation, because this is kind of sophisticated manipulation on a planar environment, and then you imagine scaling that to multiple fingers, and you've got, in principle, some quite complex. You could get some quite sophisticated ways of interacting with objects. So as I emphasized, just using a sense of touch, there's no vision here. It's kind of like blind pushing an object, and that appears to be cracked with this method. So in-hand manipulation, we're a bit behind where we are with prehensile manipulation, but because of the extra difficulties in getting these methods to work on robot hands. But where we are, so Effie's done some work recently on in-hand, a controller for stabilizing grasps with a fully actuated robot hand here. So this is kind of using similar servo control methods, but instead the control now tries to stabilize holding the object, and then once you've held the object, I mean, Effie's taken this work forward into how then you can manipulate the objects and move the pose of them around in hand, which is something she's working on at the moment. And then say we're also moving into integrating with anthropomorphic human-like robot hands. So one of the key things to notice here is that we have the sensor down at the same size as a human fingertip. So that was a key developmental advance, because obviously that's a route that wasn't possible before, but it's clearly a key thing for using on realistic hands. And then there's a kind of basic example of in-hand manipulation here, just to kind of validate that the sensor's working. But this is, again, something we're taking forwards. Okay, so I'm going to finish on tactile skill learning. So this is a different way of approaching the control of touch. So again, we're using deep learning, but now we're using instead deep learning to predict the actions rather than trying to perceive aspects about the input. So it's trying to tell it predicts what the robot should do. And then to train this, we're using deep reinforcement learning to learn a tactile skill. So you're just using reward to shape the task. So if you give a robot a task, say pushing an item around, and then if it does it properly, it's given a reward, told good boy, or girl, and then it tries to hone its action selection system in a way that it will get the most rewards in the future. So these same methods that DeepMind used, and actually this work was in collaboration with DeepMind. So these are same methods have been used to play Go and beat humans at Atari games, etc. But here applied to tactile robot. So this is what Alex Church has been doing in his PhD, say co-supervised with DeepMind with Raya Hadsell. So firstly, this is first demonstration in the field of deep reinforcement learning. We're working with a tactile robot. So this was learning to type on a Braille keyboard. So the robot needed to learn the layout of the keyboard and the keys, and then in order to type, which it took it a couple of days to do, but it got there. So that was published last year, and then just out is Alex's latest work. So now instead the robot is trained completely in simulation. So it hasn't been near the real world. It's just with Alex set up a simulated environment on a fairly basic computer. It's not that advanced simulation. Trained the action selection policy completely in simulation, and then through some clever machine AI methods, transferred that policy to the real world, and then it works first time on the robot. So basically the tasks that I was shown before that we could solve, that we addressed using more standard machine learning methods, and can now also be done, can now also be learned using deep reinforcement learning in simulation, and then it just works first time on the robot. So we see this as kind of a key step, because the challenge of applying deep reinforcement learning to robotics is the amount of data it needs to train. In learning how to play Go, they played literally millions or hundreds of millions of games to get the robots to learn, to get the agents to learn. In this, that's unrealistic on real robots because they have to work in the real world. But this is a technique that then enables that to happen because they can learn in simulation and then transfer that to the real world. Okay, so I can see I'm running out of time. So I just want to do some take-home messages. Robot dexterity using, or shall I finish now?
No, fine. No. You still have 4 minutes. There's one question in the chat as well, but please do your take-home messages, yeah, and then we maybe have time for questions. Yeah.
Okay, so this will take about a minute to 30 seconds. So take-home messages. Robot dexterity using touch is still a pale shadow of human dexterity, but as you can see, I mean, all that progress I've talked about that happened in the last year and a half or so, and then this is one lab, my lab. There's about 15 people at BRL. At Bristol, there's a whole world of people working on this field who are also moving very rapidly as well. So this is really starting to look achievable as a goal, and I would see this as happening this decade. I'd say so. Research in this field is moving very rapidly. Deep learning appears to be the key to unlock human-like dexterity in robots, and that in our lab that perfectly complements our use of soft biometric optical tactile sensing. And then I want to say thanks to the people who actually do the work rather than just talk about it, this is my group. So thanks, and thank you for listening.
And thank you, Nathan. I have to say, every time when I walk by the base you have in the lab with your group, it's always great to see the robots taking data samples of the shapes and everything. So it's I always enjoy that. So we do have one question from Alex. So Alex asked, what kind of sensor update rate do you have with the, I guess with the tough tip sensor or with your sensors in general?
Sensor what rate?
Sensor update rate.
Sampling rate. Well, I mean, we have a camera in it, so it depends upon the frame rate of the camera. So for off-the-shelf cheap cameras are roughly about 100 hertz frames per second, but you can pay more money, and then you can get ones up to a kilohertz. There's work on neuromorphic cameras. Ben Wood-Cherrier uses neuromorphic cameras, and they basically don't have a frame rate. They sample events instead, so that's kind of an infinite frame rate, if you like.
Great, thank you. So I also have a question. So as I said, I walk regularly by your bay, and I see, because I'm not from the field, I'm not, I don't do anything with tactile robotics. So when I see the robots taking the samples of the shapes, for example, that is quite logical to me, someone coming from human-robot interaction, that because you have the deformation and then you take the pictures and then. But I saw recently that you also did some tests where you had different types of cloth. So, I mean, something like this, and then you had something with little straps and so on there. So, is that how well does the tactic work to recognize cloth and other materials?
Well, this comes down to the question about frame rate earlier. So that's due to that. So there's several ways of doing this. I mean, one of the ways we're looking at is having a vibration sense in the sensor for feeling texture. And that's actually how human skin works. We have a separate vibration sense from, if you like, our geometric and slip senses. So it's under investigation. But all of this is needed for, like the holistic sense of touch that we have.
Yeah. Yeah, great. All right, I think it's bang on time, 2:30. So thank you, Nathan. And we will switch over to Professor Farid Dailami now. So I'm going to add Farid to the stream now. And there we are. Hi, Farid.
Good afternoon. Good afternoon, everyone. I shall start my slides.
Yeah, and I'm going to add them to the stream. Yeah. So Farid, over to you.
Thank you. So good afternoon, everyone. My name is Farid Dailami. I'm Associate Prof in Bristol Robotics Lab. I run a center called RIF, or a unit within BRL called RIF, Robotics Innovation Facility. And basically our task is to try and assist anyone who is interested in robotics and automation in reaching their goals and their aspirations. So the actual place that it's a physical place. So I'm actually sat in my lab at the moment. So when you look around behind me, these are the pieces of kit that we have. So we tend to all the time work with industry and academia outside of BRL. So we are an out-facing facility within BRL. We have lots of machinery and hardware that we can use, and also we have a lot of expertise in our little unit, but also we have access to expertise within BRL. So we're very fortunate insofar as we can help those who want to look at automation, robotics, digitalization, etc., by enabling them to come in, talk to us. We can demonstrate ideas using robots. We can talk to our colleagues in BRL and essentially try and get a synergy with both hardware and software and expertise, etc. So it's a very useful place to be for those who are aspiring to go into robotics and automation. Currently, we're running 3 different projects. So at the moment within RIF, we have something called RIF Saver, which is an ERDF funded project, and that allows us to provide within close proximity to Bristol, provide free service. I'll talk about that in a second, a little bit more. We also have something called TerryNet. This is a pan-European project. So if you wish to do some robotics, and for example, you want to do some, say, medical, you're developing a medical instrument, we have colleagues in Italy, so that you can contact them through us, and you can then go to Italy and do some very early stage work, and you will get reimbursed for your travel costs, etc. It's an excellent mechanism. So please come to us if you have some ideas about the sort of robotics that you want to do, which is very advanced. It's around PhD type application. So come to us and we'll search around to see whether or not TerryNet can be of use to you. We also are running a project at the moment with Rolls-Royce, where we're looking at using robots for welding. Again, this is something that is funded for about 3 years. So we do run a number of projects, and we do engage with both application, but also research in those areas. One of our main concerns really has been all along is addressing SMEs and SME needs, both in terms of wealth creation, but also in terms of job creation. SMEs are the primary mechanism by which we earn money in the UK and by which we generate jobs. So for us, SMEs, and for the government, and also for the European Commission, SMEs are key to the wealth generation and the health of economy. So we tend to be focusing on them quite a lot. They're normally not very well off in terms of funds and finance, and also they tend to be firefighting most of the time. So if we can help them, then they are, if you like, our primary customer. That doesn't say that we don't engage. As I said, one of our projects at the moment is Rolls-Royce. So we do engage with all manner of companies, but SMEs tend to be quite important to us. And to some extent, this is the sort of thing that we're trying to help with. When you're looking at technology maturity, we can start in a lab and we can develop ideas, and there is funding available, etc., etc. So we can sort of get ourselves up to around there with funding. But then once we're at that stage, funding dries up. And this region is called Valley of Death, when good ideas can actually die because there is no monetary support. So what we tend to do, we try and see if we can bridge that gap with the capabilities that we have, with some funding that we have. So we've gone, if you like, beyond the stage 3 and 4. We're trying to get ourselves TRL 5 and 6 to try and go across this funding gap, and then hopefully we can take the company, the product, etc., up to that stage where they can start to become a business success. In terms of knowledge acquisition, knowledge embedding, and exploitation, which are the key stages of innovation, and that's what we're trying to do. We in RIF are very good at identifying what sort of knowledge you need in terms of implementing robotics and digitalization and automation. We have access to, as I said, lots of expertise inside RIF and outside to enable you to up, if you like, your awareness of what knowledge is available in order to then try and put that knowledge into your product or your processes, and hopefully get to a stage where you can do exploitation, and then you can claim that you have an innovative process or an innovative project. So RIF again is very instrumental in meeting that very early stage knowledge acquisition. In terms of funding, what SABRE, which is the current program that's running, we have about £1 million. We've had about £1 million, and we will finish around September of 2021. But there are efforts afoot to try and extend that and go for another 2 years if we can. It is, as I said, centered around Bristol. It is centered on SMEs. So if you're an SME and you're in this area, then please, if you have some ideas in terms of automation and robotics, please do contact us, and we might be able to help you and try and enable you to get your aspirations, basically. The kind of product that we have is we do a 2-day workshop. So we bring you in, we talk to you about robots, we let you play with robots. So it's not a question of just chalk and talk. We actually, the core of it is for you to get experience in terms of robotics. So if you have some interest in that area, please do contact us. And at the moment, obviously, COVID has caused some issues with that, but as soon as that disappears, hopefully we'll get back to normal and be able to start having physical workshops in this place. But do contact us so that we can start to put you in our program. The other mechanism that we can engage with you on is called a technical development project. Basically, as an engagement, we can work with you from around 5 days to 12 weeks. So if you're eligible for SABRE support, then this is something that we can do with you. We can do feasibility, we can do prototype development. There are many mechanisms by which we can engage with you. So in terms of some case studies and some examples, here's an example of somebody who came in. Basically, what they do, what this person does, is develop natural history footage. And some of the areas that he works in are producing footage for in terms of insects and ants and stuff like that. And basically, what he wanted was to try and capture footage of, say, ants moving around on a bark of a tree. And he was saying that it's very difficult to do that at very close quarters with a handheld camera. And would it be possible, and he didn't know at the time, would it be possible to do something with a robot? So we looked at that particular problem. We asked him to bring in the sort of cameras that he would use, and we mounted those on one particular robot and programmed the robot to scan an object. And we found out that vibration was a big issue, and we were getting very poor images from that process. So then we moved from that to our biggest machine, which is a 60-kilo payload KUKA robot. And when we put the camera on that machine, obviously it was very steady and the images were excellent. However, this is a very large and expensive machine. So we then contacted KUKA and we said, well, this is what we're trying to do. But the big machine, whilst very steady and very solid, it's too expensive and too big for what we want. So we managed to work with them, and we borrowed a robot from KUKA, much a smaller robot, but nevertheless still with a very similar kind of rigidity. And we brought that in and put the camera on that machine and developed the software and ran that that particular arrangement of camera and smaller robot, and we got excellent footage. So the company was then thinking, okay, we can get this, and they did. It was affordable as far as they were concerned. It wasn't a brand new robot; it was a reconditioned robot, but nevertheless, it fulfilled their requirements. Now they have one of those in their place, and they can do various types of footage, and just as an example of the sort of thing that he's been doing. So he's not a roboticist, but he's controlling that robot with some of the software that we produced for him, and now he's capable of. This was a trial. He's capable of capturing excellent footage using that particular system. So that was a huge success. He's delighted with what he's getting. We had another company that came in, and they are again a startup. They were looking at laying down composite bands, white bands in manufacture of composite components. They have a very new process whereby they can, if you like, shear the fibers as they're laying the fibers down. That will allow them to change direction of motion and will allow them then to basically produce complex shapes. And they came to us and they said, this is something that we want to do, but we're not quite sure how we integrate our end effector that sits on the end of the robot with a robot. How would we go about that? And we addressed that. One of our engineers looked at that, and we did the integration. And what happened after that was that we now have this kind of demonstration. You can see the shearing is taking place, and the direction is changing without wrinkling or introducing other defects in the layout. So this again has proved extremely useful. Without the existence of RIF, it would have been difficult for ICOMAT to have progress as far as they have. So this is another example of the kind of thing that we've been able to do. We've recently been working with a company that produces a gap measuring kit. So if you imagine you have a car door and there is a gap between the car door when it's shut and the body. So one of the applications is that their laser-based equipment can actually measure the gap and the depth, but they wanted to mount it on a robot. So they came to us and they said, well, we know we can hold this device by hand and we can scan, but we want to automate the process. Can we do this? And again, we demonstrated for them that yes, this was something that we could do. In the process, we collaborated with Universal Robots, and Universal Robots have developed an intermediate set of tools that will allow developers develop interface tools between what the end effector tool is and what the UR system is. And we have developed that kind of interface for Third, and that again has worked out exceptionally well. We have a little video from UR.
Hello everybody, my name is Stefan Kollmannsberger and I'm working at the UR Plus team at Universal Robots. We at Universal Robots aim to enable access to automation to everyone. With this in mind, our cobot is laid out to be programmed so easily Also, non-robot experts can create their own applications. We include a wide variety of safety functions to reduce the time for a proper integration substantially, which can even allow to work the cobot side by side with its coworkers. As our cobots integrated in a wide array of different applications, they always interact with different third-party products, like grippers, camera systems, linear access, etc. The integration of these parts alone could take days and needs expert knowledge to implement, which is in contrast to the overall UR programming experience. To counter this, Universal Robots created the Universal Robots Plus Partner Program, or short, the UR Plus program. The UR Plus program behaves like an ecosystem of plug-and-produce products, which are validated and tested by UR to assure compatibility and ease of use with our cobot, and are focused on our customer needs. This means we support our partner companies all around the globe, integrating their products into our cobot. With this, by purchasing a UR Plus product, you do not only receive the needed hardware to connect directly to the UR, but also get a piece of software, the so-called UR Cap, which is tailored to the product's needs, lives within our teaching environment, and offers you the same easy programming experience as the UR itself. Since introduction in 2016, the UR Plus ecosystem grew steadily, with now over 200 UR Plus products available in Europe alone. On this journey, we also met the company Third Dimension, located in Bristol, and the Bristol Robotics Laboratory. Third Dimension offers great non-contact profile measurement solutions, which are also fitting for being operated by a robot. Seeing the opportunity for a collaboration, they reached out to us and we started the process of becoming a UR Plus partner with them. During this, the Bristol Robotics Laboratory helped Third Dimension by developing the UR Cap, the software controlling Third Dimension's tool through the Universal Robot. It was an outstanding experience working together with the Bristol Robotics Laboratory and Third Dimension, as they were doing an excellent job integrating their product in the UR and offering an elaborated and easy-to-use solution for our cobot. Thanks to all the colleagues of Third Dimension and Bristol Robotics Laboratory for allowing us to be part in this great journey. We're looking forward to having this product in our UR Plus ecosystem soon. Greetings from Munich and all the best. Bye.
So that's an example of the kind of thing that we can do with both, if you like, a robot supplier and a client. We can really go deep into that collaboration and develop very, very, very useful tools to allow very quick programming of end effector tools. And both the one with Universal and the one with KUKA have proven that, yes, we are well capable of developing facilities for people who want to use robots. We also have worked on much bigger projects. This one was with Pneumatic International, people who make vacuum cleaners. And this is an example of the kind of thing that we got engaged with, again, very deeply, trying to figure out how can we reduce repetitive strain injury and allow the company to improve its productivity. And this is what we did. We developed robotic application, again, using various tools to try and explore potentials for looking at assembly of vacuum cleaners. This was then taken into the shop, the development shop at Pneumatic, and they developed, with our guidance, they developed this particular assembly process. And we got to a stage where we could demonstrate the effectiveness of this process. And now what you see on the screen is a version of that is sitting on the shop floor, producing vacuum cleaners, assembling vacuum cleaners. They have found this particular setup to be so effective that they have now replicated it 4 times. So again, it's been an excellent example of, in the right application with the right process and the right type of investigation, you can develop very effective automated and robotic solutions. And this is what we have managed to do with pneumatic. Some of the key stats as far as Sabre is concerned, we've well, as far as the whole RIF is concerned, really, we've helped, as the numbers there show, lots of companies to get engaged with robotics and automation. And one of the good numbers is that we've gross value added number that we have is around 22 million. It's not been over a couple of days. This has taken quite a while. We've been doing this sort of work since 2013, so it's taken a long time to get to this place. But nevertheless, we think we are very, very effective in developing solutions, automate solutions, which are industrially viable. And these are some of the comments that we've had. I've highlighted really the parts of the comments that I think are key in red, and how we have been, if you like, instrumental in helping a lot of these companies. As I say, not all SMEs. There is a comment from Sandy King from Rolls-Royce, as well as a startup, Benedex, and also Indus4. And with that, I am going to stop and see if there are any questions.
Thank you, Farid. So yeah, I mean, to the audience, if there are any questions to Farid, please put them in the chat, and we will. So we do have time to answer them. In the meantime, I have a question to you, Farid. So I mean, since my main research area is human-robot interaction, so in human-robot interaction, maybe 8 to 10 years ago, there were many funded projects that all looked at how companies can use industrial robots for a setup where you have a assembly with a human and a robot working together on an assembly task. And the idea was always that you say you use the efficiency of the robot and the quality and the precision of the robot together with the human being more flexible. So, for example, for lot size 0 or lot size 1 assemblies where you only have one product and you want to build it with a lot of precision, so that you say the human is instructing the robot to do things, for example. So as I say, 7 to 10 years ago, there was a lot of funding for this kind of research. So my question is, are any of the industrial partners that come to you and come to talk to you and the RIF having these kind of problems? Are they asking you how do we bring more humans and more human-robot collaboration into our factories, or are they more looking at automation?
No. Good question. In fact, when Pneumatic approached us in the first place, they said, we have heard that robots and human beings can collaborate, and that's what we're looking at. Mm-hmm. That's what we're interested in. So when we started the work with them, one of the very earliest stage ideas was that the robot would hold a part of the vacuum cleaner mm-hmm. in front of a human being, and that human being would then start to put in the cabling. You need the dexterity and the visual capability of a human being to handle some of the very fine work that you need to do in some cases. Mm-hmm. So they were looking at that and they said, we think this is going to be what's needed. But when they did their analysis, they found out that really wasn't where the biggest concern was going to be in terms of the gains that they would make. What mm-hmm. they concluded, as I said, was the repetitive strain injury that their people were subjected to, and also mm-hmm. lifting of heavy components. So what their major concern was, we have human beings which are gradually getting towards the end of their useful working life, if you like, mm-hmm. but we don't want to lose them. we want to keep them because they have lots of expertise and we want to keep them. So how do we actually keep them? Well, what we can do is to try and make their lives easier. And the way that they did that was to remove the idea of a human being doing the fastening, to remove the notion of a human being picking up stuff and putting them in another location. And those approaches went down very well with the shop floor, because the shop floor then realized that in this particular instance, automation wasn't threatening their jobs. In fact, it was helping them. So there are situations where people have asked, can we use this combination of a human being and a robot to work together? And for me, in a sense, that is where we want to go. That's where we want to be. We want to this idea of cobots and enabling humans and robots. Clearly, one of the big issues is going to be the handover. At what stage do you say to the human being, yep, you can now hand over to the robot and hand over from the robot to the machine, etc., etc. So all of this needs further investigation. And one of the works that at the moment we are doing with Rolls-Royce is very much centered around that. So you have an operation taking place, there is a welding operation taking place. Somehow you have to give some information to a very skilled welder, and we don't know how. And that skilled welder will then need to have some capability to go back to the process and alter that process if he or she thinks that there are some modifications that could be. How do we do all of that? We still don't know. We don't have the sensing. We don't have the capability to do that. So this is a big issue for us to resolve. Yes.
Yeah. I see we have a question in the comments here. I'm going to show the question. So it's by Nayab Ahmed. He asks, once a company has developed and implemented a robotic solution, how do they keep the development process sustainable, as it may not be their core business?
Excellent question. That is very much the case, and this is where we do find lots of challenges with companies that do go along the automation line. If they don't have in-house support and they're relying on the supplier, the system integrator, to come in and support them when things are not going right, that can be problematic, and it is problematic. So one of the key concerns that we have, and one of the key ideas that we try and inculcate in companies, is not to go in and provide a solution, is to go in and provide the knowledge and transfer that knowledge into the company, so that the company is then capable of looking after that particular piece of kit. That's, for us, that's a very, very important part of our engagement. So we're not consultants who come in and give you a point solution and walk away. We're people who come in, work with you to provide the solution, and stay with you as long as necessary for you to be able to support yourself. So that's a very important and a very key question in terms of digitalization, automation, robotics, etc.
Exactly. I mean, I guess the longevity of the solutions is also really important for a company, and for the risk they are taking of adopting a new technology like robotics into their processes.
Yeah. And one of the key things that we say is we try and de-risk the whole investment in robotics. We try, that's one of our key statements right at the very beginning. We will look at your application, because there are lots of applications. People say we want to robotize this, and you look at the application and you say, well, why? This is not necessarily going to make. It's not going to be profitable. Don't do it. So I run something else called the smart automation. And in smart automation, the first question is it smart to automate? Never mind what technology can we use to automate, but is it smart to automate to begin with? If you haven't got a question, if you haven't got a good, clear answer there, then don't bother.
All right, thank you, Farid. We are right on time, so thank you for this excellent talk. And so I mean, to the audience, if you have any more questions, there all the information how to engage with Farid and the team from the Robotics Innovation Facility is all on the website. So please have a look there. Thank you, Farid.
Thank you.
All right, so we are moving on to the next talk, and I see the speakers from the next talk are already there. So hi, Severin. Hi, Nigel. It's very good to see you. Hi. Actually, just behind me, in the room behind me there. So Well, yeah. I'm handing over to you now. Let me just load. Do you need your slides at the beginning? Yes, I guess.
We can say a quick hello to everyone first. Hi.
Yeah.
It's a great pleasure to be today presenting our work with my colleague Nigel from the Department of Education. I'm myself Sylvain Lebignon. I'm Associate Prof here at BRL in Social Robotics and AI.
My name is Dr. Nigel Newbutt, and I'm a Senior Lecturer in the Education Department here at UE.
For the last, 10, 12 days now, we've took a paper robot, exactly like that one, to a school, a local school. Nigel will tell us a bit more about that in a minute. A school that hosts autistic children. And our question was, what can we do to support the well-being of those children?
Yep. So yes, as Severin has already introduced, we wanted to take Pepper into a school, specifically a school for autistic children. And we wanted to understand a range of things. We wanted to understand how a robot could integrate into the school ecosystem, as we're calling it. So the school as a whole, not just the classroom necessarily. And we also wanted to understand about how the children wanted to use a robot like Pepper in their school. So that led us really to be underpinned by working with the pupils and the teachers before we started doing any work in terms of programming or proposing what the robot may or Pepper may do in the school.
So one of the things we really kind of put a lot of effort on and a lot of time on is trying to have this kind of participatory design approach. So,
but before we get to that, this is where the school's located. It's in Somerset, about 25 miles south of Bristol, which is where we are at the moment. It's considered a rural school, actually. There's 144 pupils, and it's a fairly newish school. It's 4 or 5 years old now.
Yeah. So the main idea was, how can we come up and design a robot, a social robot behavior that makes sense for those children?
So one of the challenges within sort of robots and autistic research in particular is that it's often led by researchers, and it's often led by researchers framing the problems and wanting to think about how the robot may be used, a robot like this may be used. But what we wanted to do was to learn from the pupils themselves how they might like to see a robot like this used in their school. So as Severin has already said, we were engaged with a co-design or participatory design methodology, and we spent a day in the school working with some pupils, and we actually asked them their views. Pepper demonstrated a few of the things Pepper could do, and then we asked the pupils to give us some ideas on how that could actually be articulated into what they may find useful in the school for them. And as you can see here from a mind map that we captured after that sort of process, that the students or the pupils reported that they felt the robot may enable them to regulate their emotions and connect with their well-being in the school. So that's the information that we took forward into terms of building some interactions with Pepper.
So we went back to the lab, all these ideas that were coming directly from the children. We also talked to the teachers. We also talked to some other autistic adults to get their additional feedback. We went back to the blackboard, to the whiteboard really, trying to come up with a way to program that into the robot. So you have this beautiful picture of Nigel in front of the screen and us mind mapping a behavior. What you might be able to see on that screen as well is this column of blue little boxes. Do you want to tell us more about that?
Yeah, so when we worked with the pupils, and as Severin says, rightly so, the teachers as well, we actually learned from the school that they have a range of ways of getting the pupils to articulate how they're feeling at any given time, range of being very happy and being very relaxed, right the way through to being maybe a bit angry and a bit frustrated. And so what we did here was we identified that an individual interfacing with Pepper through the screen here could actually articulate how they were feeling, whether they're feeling happy, angry, sad, motivated, unmotivated. And when we worked with the teachers, they gave us some interfaces that they use, and we were able to integrate that. So essentially what we designed with the pupils was an interface that they can say how they're feeling. Based on how they're feeling, they're then presented with a range of options in terms of interaction options that they can interface with Pepper through.
Yeah, exactly. So we had those 4 big categories of, let's say, feelings, moods, and then based on that, we created this kind of behavioral tree that would lead to a set of activities. So you can see on that screen some of those activities. One thing that is quite important to say is that even though the robot is overall autonomous, we are not teleoperating it when it's operating in the school. Everything is child-led. The robot will suggest activities, but it's always down to the child to decide what they actually want to do.
Yeah. And I think it's also, I don't know if we've got any pictures coming up, but it's worth pointing out that the pupils actually told us, or we proposed that being in the classroom may be something that they may see Pepper being useful, but actually they told us being in the corridors of the school and being in communal areas of the school were where they preferred to potentially interface with Pepper. So we position Pepper in the school, or Pepper's currently in the school, in the corridors, near the lockers and the bathrooms, and the pupils are actually coming out of the classrooms to interface with Pepper at various points during the day, both during break times, but also during formal teaching times when the teachers are sort of enable the pupils to go out and interface with Pepper.
And that's actually something really important. Between what Nigel just said and the activities you can see on the screen, it's quite important to explain that contrary to a lot of previous research on robotics and autism, where robots were usually used to kind of teach social skills to the children, our approach is quite different. We are really focusing on well-being. And one of our colleagues, the third colleague who is not here today, Louis Rice, is an architect working on how a building or a space can support well-being. And he has also been a really important piece of the puzzle there. How can we design a robot, a social robot, that lives not in the classroom, but in the school, in the corridors, and support the well-being of the children?
Absolutely. Yeah.
All right, so we did spend a few weeks programming the robot, and then it was time to actually get to the school. So we loaded the robots in the car. Yeah. On that picture, you can see, so on the left-hand side, Louis, the third of our colleague, and in the back, Joe, who is also like a PhD student who is helping us to record and observe all the interactions. Yeah, so we went to the school, and we're going to show you a quick video, a 2 minutes long video that was filmed last week by the media team here at UWE that shows a little bit what was going on in the school.
Hello, I'm Pepper, a social robot from the University of the West of England. My researchers are sending me to the Mendip School to live there with the children for 3 weeks. Exciting!
So the project involves bringing in a social robot called Pepper into a school for autistic children to help them with their emotional well-being and also with their learning.
This project, first of all, positions autistic young people at the centre of the research. And what we're looking to do is understand from them how a social robot can be embedded and utilised in their school. And we're currently in the process of evaluating what interactions the young people are having.
Hi, good to see you. What do you like to do?
The robot is programmed to first ask how the children feel. And based on that, it will offer a range of activities. It can be like maybe telling a joke, but also some children told us that they like more calming activities.
Would you like to listen to some music? Or I could do a cuddle?
Good. Calms you down. Actually does. Pepper can tell a story, do fun dances, just listen to you, play music. Stuff like that. I've been listening to some of her jokes. They're not hilarious, but they're not boring. They're moderately funny.
Joke time. Why did the kid cross the playground to get to the other slide?
Now that was a good one.
Pepper allows us as teachers to provide opportunities for our young people that aren't ready to have social interactions with other adults yet. Children have reacted to Pepper in a number of different ways. Some of it has been really positive. There's been a lot of dancing that's been taking place. We've seen increasing numbers of groups around Pepper. So children that wouldn't normally socially interact with each other are now interacting with each other.
The aim of this project is not to look at how robots can potentially replace teachers, but rather listening to autistic voices and the teachers in terms of how this tool can best support them in this setting.
Goodbye. See you soon, and thank you for watching.
Excellent. Cool. So that gives you a bit of a feeling for what is actually happening. Like the robot is still in the school until the end of this week, and so even though it's a bit too early to draw like final conclusions, we thought it'd be nice to show you some initial results. Yep. We were recording on the robot every time an interaction took place, what the children did with the robot. So 12 days in, 2 days to go, what have we learned? The first thing, which is probably quite expected if you've been working with robots in the past, is that there was a lot of excitement at the beginning. So in the first couple of days, like you can see here that the robot was used a lot, like up to 2 hours per day. The robot was actively being used by the children. And now, like over the last couple of days, we can see that this went down quite significantly. So we're talking about less than an hour of interaction. That is not a surprise. That's something very well established in the literature in social robotics, this novelty effect. The real question for us now is, for the last couple of days, are we going to maintain a level of social interactions, a level of interactions? And if so, what are those interactions? Because that's a real question we are asking. Those children who are still interacting with the robot after 3 weeks, they probably need something from the robot or are looking for something with the robot. So that is really the focus of those last few days.
And one thing that we've also noticed across that picture, which I'm not sure if the next data set elaborate, but we've noticed that there are similar pupils returning to the robot now. So initially there was a lot of different pupils arriving at the robot to interface with the robot. Now, although that's tapered off, there are more similar people coming back to interface with the robot. So we're trying to, as Severin says, try to understand why that's happening and what that's happening and what they're really seeking to do with that. So that, and while these charts are lovely, we're going to then make sure we go back to the school after to capture some of that qualitative voice of the pupils and the teachers as to why they were doing it.
Absolutely. So that graph kind of relates to that as well. That's a typical day from 9 to 3, like the day, the typical British day. And that graph shows there's 1 line per day, how many children interacted in total since the beginning of the day. And you can see that at the very beginning of the study, we had like a lot of children, like up to 70 interacting with the robot, while we are now like down to around between 20 and 30 children. That kind of reflects the fact that a lot of children are less interested now, but we still have like a core group of children that are trying to interact. Yeah. Another kind of fun graph to look at is what kind of activities the children do. And as you would expect, fun things like fun dances are very popular. However, we can also observe that if you take together all the kind of more calming activities, so like the calm dances on your left, the calm music, maybe the relaxing sounds, if you sum them up together, then we would actually observe that we are at the same level of interest. So the robot is used as well by the children to kind of calm down and help them to manage their emotional state.
Yeah, and I think it's important to point out as well that the pupils, although calming is very important in terms of being quite heightened and excited to help to reduce those activities, actually it's important to point out that actually sometimes children need to be kind of excited and sort of G'd up and to be got into that sort of zone. So obviously these sort of some of these activities are pointed towards the fact that some of the children are using them to sort of calm them from a state of excitement, but also using it to actually excite them as well, to get them into a place where they're ready to learn as well.
And maybe a last graph that is quite interesting. If you remember, every time that a child starts to interact with the robot starts by asking, how do you feel today? So we had like 4 big groups, like, oh, I feel happy, I feel maybe a bit sad, a bit down, I feel frustrated, or maybe worried, or I feel angry. So that's the green, the blue, the yellow, and the red you see on that picture. And what we see on that graph is their initial state, and when the robot is asking them at the end of the interaction how they feel now, how that mood has evolved. And the picture is a bit messy. There is no clear take-home message yet. We need more time to look at that. But it's also already quite interesting to see that quite often if they start happy, they are still happy at the end, which is kind of reassuring. Sometimes if they are sad or frustrated or angry, they feel better at the end. But we also see the opposite. Like sometimes they started like very happy and they look angry at the end. So maybe it's because the robot was not working as they were hoping the robot would work, or maybe they were just randomly clicking on buttons. They've done that a lot as well. So we need to clean up our data a little bit. But that's also something we are looking into as a way to measure the efficacy of the intervention, essentially.
Yeah, and I think it's worth pointing out that our researcher Joe Dailami, who's in the school, sort of helping us to capture these interactions, both mostly automated through a device and an interface that Severin's designed, but also he's trying to pick up on those sort of returning pupils and trying to sort of gain some insight as to why they're returning.
And even like beyond that, I think it's important to also say that we are not only interested in numbers and figures. What a lot of our work is also to build up this kind of qualitative assessment of what is the impact of the robot on the school.
Yeah, I think it's important to point out that this work it's positioned in a sort of co-design context, but it's also sort of triangulating data points. So we're really keen to bring about the quantifiable information in terms of how many times people interface with the robot, what type of interfaces they had, but also why they had those interfaces. So we're looking to triangulate the voices of the autistic and the pupils and the teachers. And this slide, as you can see, just kind of highlights some of the sort of feedback we're getting from this being awesome, from this it being not so much about what the robot does, but what happens because the robot's there. Somebody saying that they would never have said that she was scared, and one of the boys had a big breakdown in the PE session, was a non-starter for him, and the robot helped to bring the pressure down, so helped to relax that pupil. But also we've had comments where people have suggested the robot's a bit creepy and they don't like it, they want it turned off. And it's worth pointing out that we've worked very closely with the teachers to manage that situation with that particular pupil, child in that class. And so we've been very responsive and very adaptive to how we've used the robot in the school. So this isn't just about plonking a piece of technology in a school and saying, there you go, let's see what happens. But we're being very responsible and very sort of ethical, I guess, in our approach in terms of how we're working. And after every day at the school, we debrief with teachers. We understand what may have gone well, what may have gotten not so well, and then we're able to respond to that accordingly. So the child that said that they found the robot creepy and turned it off, we've just worked very closely with that pupil and the teacher to be reassured that keeping the robot and the study going has been appropriate.
And at that point, I also would like to acknowledge the contribution of our colleague Vicky Sharizi, who is working for the EU, but with the UNICEF as well. And we've been looking at with her at how we can design a process, a methodology, and ultimately a robot that respects the children, is ethical, is responsible, takes into account the best interest of the children. Sorry.
Yeah, so this is very much about positioning children's voices centrally and making sure we listen to those and have those come out of the research that we're doing. And as you said, Vicky's very interested in supporting that work and having that work inform the future of sort of child-robot interactions, I think.
So we still have a couple of days to go, well, until the end of the week, really. Yeah. Hopefully in the next couple of weeks, we will have like a really good look at the results, trying to draw a few conclusions. Can a social robot like Pepper have a positive impact on a school for the well-being of the children, for the general dynamics of the school? And the answer might be yes. The answer might be, well, maybe not so much. That's really what we're trying to look into now.
Absolutely, and hopefully you've been able to sort of hear some of the sort of anecdotal evidence that we've had so far, some of the more robust evidence that we've had in terms of the quantifiable information. But I think it's also important to point out that the teachers' responses, as I said, we've been catching up with teachers every day, and they're still reporting sort of a positive aura around having this type of technology in their school, and they're already talking about ways that they can continue with this type of technology in their school. So I think one of the benefits of working in situ, as I call it, in the school, is that teachers really get to see the benefit of this stuff, and they get to see what some of the challenges are around it, as well as those benefits. And there's a proposition, I think, that the sort of uptake and the sort of articulation of this work into practice is better adopted if we work in that way. So that's another reason that we've taken Pepper from the lab and worked in the school, which is sort of really important, I think, to underscore.
But thank you very much for listening. I think we still have time to take a couple of questions. So please drop them down in the chat, and very happy to answer.
And I see Pepper is also saying goodbye there. So yeah, thank you for a great talk. Thanks, Nigel. Thanks, Søren. So we do have questions in the chat, and so I'm going to show the questions. So the first question is by Sally Hall, and she asks, or she says, great talk and interesting product. Wondering the choice to make Pepper look semi-humanoid. Is there a move to make Pepper less or more human-like?
So it's probably quite important to start by saying that we haven't built ourselves that robot. So Pepper is a robot that we can buy, made by a company called SoftBank Robotics, based in Paris. You're right, the design of Pepper is indeed anthropomorphic. It looks a little bit like a human. It's not quite there yet. I think the design of Pepper is actually quite interesting. It's somewhere in the middle. I don't think there is any kind of golden rule saying like, oh, we should take a very human-like robot or not so human-like robot. You can see Tiago on my left, who is not like that. However, one thing that was actually really important for us in this study is that the robot is perceived as a social agent. And by social agent, we mean something that you want to relate to, that you can relate with, and that you can engage with beyond just, oh, I'm a fancy tablet with an expensive head. And I think that in that sense, Pepper fills that role quite well.
And I think, and just fortunately, I think Pepper's about the right height for the pupils that we're working with. Very clean sort of interface that during COVID times can be easily clean.
Very approachable as well.
Approachable. A lot of research in autistic sort of spaces with robots has been done using Casper the robot, which has a particular distinctive look, shall we say. And I think a lot of the sort of feedback through autistic individuals through that have been quite different to the response we've had here. There's something that the pupils can identify as this being lifelike, but it's not too lifelike. And so it doesn't have, I mean, one of the propositions with technology with autistic groups is that it can remove sort of a human dimension of interface. And I think Pepper sort of bridges that quite nicely. But yeah.
Thank you for your question.
Yeah, thank you.
Maybe as a quick follow-up. So I quite like your participatory approach, of course. So I mean that you ask the students what is it actually that you want and that you need. But I mean, did you also talk to the students about the design of the robot? Would they be interested to design the robot appearance?
That's a great question, actually, because we haven't really. If I'm correct, I don't think that question was raised by the children much.
It wasn't.
I think when we introduced Pepper, we kind of, willingly or not, we kind of said that, oh, that's what we're going to use. And from that point on, we were really discussing with the children what the robot should do, not so much how it should look like. And that's a really interesting question, because I was expecting the children, for instance, to tell us, oh, I don't really like it in white. I think it's a bit boring. It would be nicer if it could like more colorful, or having some like clothing. Actually, clothing is a good one. I think you did have something from the teachers on that.
Yeah, I think it did come up from the teachers briefly, but no, on the whole, there was no query about how Pepper looked. It was just they accepted that quite quickly, and we moved into how Pepper could be used in that space. Yeah. So, but that, I think, left in the school for longer, or if we were to continue this work, which we hope to, I think that would be something to potentially address.
I've certainly seen examples where Pepper was indeed in the school for a long period of time and would end up completely dressed up or colored or covered with stickers and things like that. So, yeah.
Okay, great. I'm going to come. There's a comment about SoftBank discontinuing producing the Pepper. So maybe we come back to that at the end. So, but first, so there's a question from Bruna Gerardi. She asked, "Do you have any experiences with social robots such as Pepper for elderly people?"
You may do. I do.
So, of course, social robots like Pepper, the main. What we think the main target audience for those robots is either children in schools, in hospitals, for instance, and the elderly as like social support, social assistance, social aid. Maybe I don't know if you had a chance to hear some of the talks by my colleague Praminda Kalepsoli today. If you haven't, I really encourage you to check on YouTube the catch-up streams, because she is our local expert on assistive robotics. The short answer is yes, we can definitely use those robots with the elderly. As Nigel mentioned, the size of the robot makes it especially well suited for children. So I think there's a lot of value in using that robot with children,
and just to sort of underscore the sort of elderly populations that Pepper has been used with, there's a study that has been conducted by the University of Bedfordshire. I want to say during the COVID pandemic, they've been looking at how a robot like Pepper can be used in support of elderly provision, where there's been obviously a lot of issues with with people feeling lonely. So there is a research project undertaken there which might be worth looking up as well.
Now, I also want to add one thing, which is a robot like Pepper like that. If you look at it, watch it while we're talking, it seems to be kind of paying attention to us. He's looking at Nigel right now. He has this kind of very kind of human-like, really well done gestures, However, it's important to realize that a robot like that, if you were to talk to it, or him or her to it, you would very, very quickly realize how limited it is in terms of being able to sustain any meaningful conversation. So, to be honest with you, it worked quite well for us in the school, because we have that set of activities, predefined activities, where we are very careful to limit very much the kind of the cognitive complexity of those activities. if you were to take a robot like that to your nan and hoping that the robot would be able to entertain her or that would not work very well. And after a couple of days, you would realize that the robot cannot yet do very much in terms of social interactions.
Great. We do have more time. So Alex asks, what would be the next steps for robots in the school?
That's a good question, and that's what we're still in the midst of the study at the moment, so I think it would be a bit premature for us to sort of think or, sort of share what that might be. I mean, we're just looking forward to continuing conversations with the school, with the leadership team. We're looking to debrief what exactly has happened here, what we've found.
Yeah, but very interestingly, just before that talk, we had a chat together with Nigel, like asking ourselves the exact same question: what should be the next step for a project like that one? You want to elaborate on that?
No, go well.
Okay, I think there is basically two main options. Either we keep it as it is, as a research tool, a research artifact, and maybe we'll go to different schools, other schools, maybe even the same school for a slightly longer period of time, a much longer period of time, trying to see what are the factors that make the robots adopted, but also useful for the school. That would be one approach. I think the other approach is to step back a little bit and say, well, wait. If we want to have an actual impact on the schools, on the pupils, on the society, it's not really anymore about trying to do one more study measuring how many times we've interacted with the robot. It's just to put that robot in the school, to get funding, and leave the robot there for a long period of time. Maybe with our support, with our like keeping an eye on how things are going, but trying to move to a much like an application, a real-world application, a deployment.
So that's definitely the end goal. But I think it's worth pointing out that evidence-based practices in schools are very important. So I think the continued collaboration with schools and researchers is something that needs to be kind of a thread that runs through that approach. But definitely, actually biting the bullet and saying let's put Pepper in the school, have Pepper there for the entire year, but let's have some evaluation of what's going on and what's happening, so the teachers can be reassured that there's some benefit to having this investment in this piece of technology in their school. And I think so that would be an obvious next step.
Yeah.
But of course, you can all imagine what the challenges around that might be financially and logistically and practically. And those are the things that and I think by doing this piece of work in the way that we're doing it, we're helping to overcome and address some of those barriers that have existed previously in adoption and uptake, and giving the teachers the chance just to see what Pepper does and how Pepper interfaces and how maybe easy Pepper is to support. And that doing all of those things will help bridge the challenges that teachers think that technology can sometimes bring in schools and break down some of those barriers.
Yeah, and quite importantly, I want to underline the fact that even though we have a colleague, Joe, who is there all the time for safety reasons and just to observe, the robot is autonomous. So Joe could well not be there. It would still behave the same way. So in that sense, that project, that robot is already mature enough to some extent to be deployed with its very limited capabilities to be deployed in a school. So we are probably not that far from being able to do that in a school.
That's right, but only because we've worked in a collaborative, co-design, participatory, and we've listened, we've responded, we've been flexible. Yeah, because of that, we're in a position potentially to walk away, to back away a bit more. That's right, but only because we've worked in that way, I think.
I think that's just a nice segue. What you just said, Søren, about the maturity of the product. So this is less of a question. I think it's more an answer to the question that Sally Hall asked. But the audience member with the name Kicksam said that unfortunately SoftBank recently announced they will not make any Pepper robots anymore. So any before we move on, any comments to that? Any regrets? Anything you want to say about that?
Well, first of all, what dreadful timing in terms of our study, and just in the midst of this study, and then this announcement comes out.
As a social roboticist, I've been working for the last 13 years on social robotics. I'm very sad. I think Pepper is a tremendous platform for us. Can you even think that this robot has been created 7 years ago, in 2014? Since then, there is basically no competitors. No one has been able to build a robot like that. It's quite expensive. We're talking about like £15,000, but it's actually like way cheaper than any other competitors. The robot has social capabilities that are limited, but still miles ahead of anyone else. The robot is looking at Nigel right now. You might find it's not great because it's completely like stuck on Nigel's face, but it is aware of its social surroundings.
And knows a good-looking man when he sees one.
So in that sense, I'm very sad. I think Pepper is a great platform, and I'm quite sad to see that a company like SoftBank is kind of disengaging from that research. I don't think it's going to prevent us to make further progress. There's other companies like Robotics who is trying to develop, to be an actor in that field. We will see how that worked out for them. And yeah, finger crossed, they will maybe restart or decide that maybe there is some space for them. Yeah.
Okay, thanks very much. Thanks for for the great answers, and thank you for a great talk. So we are at 3:30 now. Just time to move on to the next talk. But thank you again. Thank you very much. All right. So the last talk is actually a talk that I will do together with my colleague Paul Bremner, who is corrected now. Hi, Paul.
Hello. Sorry.
Hi. I can also add our slides to the stream. So yeah, so Paul and I are going to talk about a completely different topic. Because in our research we are we're using robots for nuclear decommissioning. We do have 2 live demos at the end of this talk. So we want to quickly give you an overview of the research that we are doing. Just a quick 10-minute talk, and then we have 2 live demos. So, well, I mean, first of all, to go into it, so maybe people are not aware of it, but the UK has actually a big challenge at hand, and that's the challenge of having nuclear facilities and old legacy nuclear facilities and nuclear waste, a lot of it. I've put a map and numbers of a official government report that came out in 2018, which says that the cleanup of the nuclear waste in the UK will take around 120 years, and it will cost the UK 120 billion pounds. So this is one of the biggest environmental remediation projects in the whole of Europe, and the UK is not the only country with nuclear decommissioning problems. Other countries have these exactly the same challenge as well. And just to give you an idea, so we think that using robotics technology for this kind of nuclear decommissioning tasks, as first of all, I mean, the potential to keep the humans away from harm, and it will cost a lot of money, somewhere in the amount of in the range of 10 to 15% of the costs. And if you think 120 billion pounds, that's a lot of money. I mean, just to give you an idea what we are talking about here, so this is Sellafield. A lot of the nuclear decommissioning legacy waste in the UK is 75% of it is located in Sellafield. This is a 6 square kilometer area in the north of England with over 2,000 buildings, and this is an aerial view of it. And so just to give you another idea, so these buildings are not simply that you can just knock them down. So we are talking about buildings that are, first of all, really compact. There are no access ports into the buildings. Inside the buildings, you have a lot of different materials. You have metal, you have concrete, you have a lot of bricks, dust. And of course, these are nuclear facilities. So they are designed so that no one can actually go inside the facility. So the kind of problems we are working with here is that you have these very hard to access buildings that need to be. And in the past 4 years, we had the luck that we have been funded by the Engineering and Physical Science Research Council. So thank you to our funder in 2 large projects. One is the National Center for Nuclear Robotics, and the other project is called Robotics for Nuclear Environments. And we're going to show you now a little bit of the work that we have done in these 2 projects. So to start off, I will talk about our work in the National Center for Nuclear Robotics on remote teleoperation for nuclear waste sorting and segregation. So just again, to give you an idea, this is how nuclear waste sorting and segregation is done now. On the one hand, you have glove boxes where people need to put their hands actually into rubber gloves to move to handle nuclear materials inside a safe glove box. And then for the decommissioning task itself, you need to need 2 humans to get into air-fed suits to go inside the facilities to actually decommissioning parts of the facilities. And at the moment, we are talking about 1 million air-fed suit missions per year in the UK alone. And all of these suits, for example, need to stay inside the facility and they become nuclear waste again. So what we are proposing to do is to have a teleoperation setup where you have a human operator using a teleoperated robot to sort the nuclear waste into containers. And the 2 things we are working on in this setup is, on the one hand, we are working on the shared control between the human and the robot. So in the end, we want to be able to have a human operator doing most of the tasks with the teleoperated robot, but we want the robot to also take over control every now and then to take over part of the task autonomously. And so the research we're doing is, on the one hand, in the safety of the operation and switching between these manual and autonomous modes. We have also done research in wireless teleoperation. So in the video at the bottom here, you can see how the robot is running as in a wired mode and in a wireless operation mode. And this is actually a collaboration where we have done collaborated together with our industry partner from Toshiba. We are also looking at the immersion of the operator when using the system. And this is, we are going to show this in the live demo as well. So on the one hand, we are interested in controlling a third robot arm that is placed in front of the remote robot. And we are controlling it with the movements of an operator that is who is wearing a VR headset. So the movements of the operator are mirrored to the movements of the robot. So the operator can actually control the robot with his own head. And also we are looking at what are the ideal conditions for the operator to receive a video stream from the camera mounted next to the robot. And for that, I've placed a research experiment example here. So we, for example, looked at ideal camera placements for this kind of robot. And I'm going to hand over to Paul now for to talk about our work in the R&E project.
Yeah, so on the R&E project, we're investigating the idea of using multi-robot teams to solve another problem within the nuclear decommissioning industry, that of mapping and characterization of sites to be decommissioned. If you go to the next slide. So within nuclear decommissioning, an early and vital stage in the process is characterization and mapping of sites to be decommissioned. So many sites, particularly at Sellafield, have reached the end of their operational life some time ago, and then they were sealed up in concrete shells until such time they could be decommissioned. And as a result, the exact layout and kind of environmental conditions need to be surveyed in order that the decommissioning operations can be planned. Current procedures for doing that mapping involve using people in protective suits and teleoperated vehicles, which can be a dangerous and difficult process with limited accessibility and radioactive contamination. On R&E, we are investigating using multi-robot teams to enable this process. So some of these 2 videos show some of the work that was done using these multi-robot teams to create a map semi-autonomously. And we've shown that mapping can be conducted more effectively and efficiently with multiple robots. And in particular, when you have a heterogeneous robot team, so that's a robot team composed of different robots with different sensor suites, and those different sensor suites can be combined together to more effectively map an area. And one of the things that we're currently looking at now is how we can enable robust communication between such a robot team, as well as with a teleoperator of the robot team. So we go to the next slide. So as I mentioned, the environment in which the robots operate is highly hazardous. So in order for robots to operate effectively in such an environment, they need to be aware of the risks that are within the environment. So those risks could be radiation, they could be collisions, communication loss, and so on. And we're investigating using a control architecture which is based on a layered cost map, where the risks in the environment are mapped onto the environment, and those are then combined in a kind of hierarchical way to influence the control decisions that are made by the robot. If we go on to the next slide, so those then risk decisions need to be conveyed along, as well as the communication information need to be conveyed to the teleoperator. So a key component of the safety case for robots and nuclear decommissioning is to have a human in the loop. So that's typically a teleoperator, but it might be a kind of a more of a supervisory role when we're looking at semi-autonomy rather than full teleoperation. And we're investigating using VR as a way of intuitive teleoperating these robots, as well as a means to display the kinds of data that they generate. So the videos that we've got there are the VR interface that I've been working on displaying data, so whether it's point clouds or it's voxels. And also we have a video on some work that a PhD student's been doing on teleoperation interfaces for controlling a single robot, which we need to extend to the multi-robot system. And through a series of user studies, we've shown the effectiveness and intuitiveness of using VR for this process. And also the benefits of being able to move relative to the data, which allows you to still recognize objects even when you've got impoverished sensor data. So robots, all the robots, as I talked about, might not have the same suite of sensors. So you might have a lack of color information because you've only got a laser scanner on a certain robot, but you still need to be able to operate on that data to be able to go, actually, I need more information about that area. Please direct some members of the robot team to this area because I need more information on this particular area. So that is the benefits that we're finding with the VR system. And what we're currently working on is being able to incorporate display of the data relating to the risks perceived by the robot team, as well as the communication information. So move on to the next. And as part of our work in the nuclear sector, we're actively seeking industry partners. So we've got prior experience in industry-funded PhDs. So fairly recently had a student complete a PhD funded by the Nuclear Decommissioning Authority. And the university has recently made more funding available for PhDs, part funded by industry. And we already have one PhD proposal fairly well developed that's in need of an industrial partner, and we're interested in finding more PhDs and more partners. As Manuel mentioned, as part of NCNR, we work with Toshiba. We've also got a project with them with Cavendish as part of NCNR, and then Sellafield are a partner on R&E. And we're seeking to continue that involvement of industry in our bids going forward. And we've got two bids currently in preparation, one that I'm working on that's looking at modulating presence. So one of the things that Manuel talked about was immersion in VR. So that relates to this sense of presence in your VR environment and how that affects how good you can be at operating that environment. And how we can modulate that using additional sensory modalities, so sound and haptic feedback. And the second is involving another program grant involving development and management of a robot fleet for infrastructure maintenance and repair. So we now have two demos scheduled. The first is a demo of teleoperated item sorting from the NCNR project, which utilizes a master follower teleoperation system where the operator moves the master arm and the follower arm copies the motions. It's an interactive demo, so you can, when you are prompted, you can enter into the chat items that you would like the operator to try and pick up using the follower arm. And the second demo is a risk-aware navigation, which is produced on the R&E project. And radiation, temperature, and collision risks are assessed by a robot, and it's used to autonomously plan a safe path. If you have any questions related to the talks or the demos, please type them into the chat, and we'll try and answer them after the demos. Finally, if you wish to discuss any of our ongoing or planned work, our contact emails were on the previous slide, actually, but we've moved to a demo view just now.
Okay, yeah, let's move to the solo layout. So, well, to the team in our test bed, if you could start the mobile robot demo now, I think that would be great.
Right.
And Paul, you're going to comment, right?
Yes.
And sorry, we also have a live view. So this is the live view of the screen for operating the robot.
So the this is a mock-up environment, a scale environment of a nuclear facility. And we have some of the barrels that are marked up in the environment, which the radioactive marked barrels are assumed to be radiation sources. The dark yellow colored barrels are assumed to be corroded and therefore have a temperature risk, as well as there also obviously being risk of the robot potentially colliding with things. So it uses all of those risks to create this layered map, which then hierarchically ranks all the risks and takes appropriate action based on what it thinks is the least risky path to achieve its navigational goal.
Yeah, and here you can see a view of this, a live view of this risk map. Maybe back to the robots. You can see the robot adjusting its strategy or how to move from one point to the other based on the risk. Going to switch back and forth between the view of the map and the live robot view.
Yeah, it's having to plan and replan as it senses additional risks, I think.
Yeah, so what you can see rotating on top of the robots is actually a LiDAR, a rotating LiDAR. And the robots are taking live measurements there of their environment. And then, so at the moment, we are not using any other sensors on the robots, but the plan in the future is to have heat sensors and radiation sensors also mounted on the robot. And we are at the moment obtaining a simulated radiation sensor that will then be mounted on the robot, because of course we can't have real radioactive material in our lab. All right, so Alex, can you move over to or point the camera to the other demo now? So thanks to Jennifer David, who is who's the main researcher working on this, on the robot maps. And now we are going to show you a live demonstration of the teleoperation setup. And Andy West asked in the chat if the robots are sharing a map. Yes, they. So at the end they will be sharing a map. At the moment, I think both of the robots are independent from, like in this demonstration that we had. But at the end, the goal is for robots to share a map. So now you can see Joseph Bollarinwa, one of our researchers. So Joseph is wearing the VR headset, and as you can see in the background, there's the camera robot, and we stream live images from a stereo camera mounted to the camera robot, and we are streaming live images onto the headset for Joseph so that he can control the remote robot there. And so you can see that Joseph is using the robot in front of him to control the robot in the background to sort nuclear waste or simulated nuclear waste into containers. And as part of this interactive session, we can now ask you to pick objects that Joseph should pick up so that you also can believe us that this is actually a live demo. So what do you want Joseph to see picking up as the next thing? Should you pick up the yellow ball, green ball, red ball, or any of the blocks there, or whatever you prefer? So please put your preference into the chat. And to the people in the room, Alex or Jenny, can you turn on the microphone from the Jabra speaker so that the audience can hear the robots moving?
Yeah,
there we are. Yeah. Yeah, we can hear you now. So the audience asks, 2 people ask for the red ball to be moved, please, Joseph. Yeah, nice. Well done there. And then, so Nayab asked for the bottle to be moved. So maybe, can you do the trick with putting one of the bottles into the other bottle? I think that's always quite nice, and shows really nice how precise the system can be used. So, I mean, to the audience, you have to remember that Joseph is not actually seeing the live robot, right? I mean, Joseph is using the virtual reality setup to and only sees a stream of the robot. So I think that demonstrated quite nicely how this kind of system can be used. So obviously, Joseph is now physically sitting next to the remote robot, but in the future, our goal would be to have the operator sitting outside of the facility with cables running into the facility, and the remote robot being away from the teleoperator. And as you can see, this kind of system is quite intuitive to use. So we have actually shown this system at a trade fair, at a conference in October 2019, and had over 50 visitors at our booth on the day who were able to simply use the robot without any problems, without any training. And I think this is really something that we are quite proud of, that you have a very simple system to use that you can use without a lot of training. So any more objects that you would like Joseph to see picked up? Yeah. So one thing I forgot to mention. So you see there are 2 barrels stacked next to the robot, next to the remote robot. There's a silver barrel and a yellow barrel, and we have actually created a virtual force field around these barrels. So Joseph, when you pick up the next object, can you try coming physically close to the barrels? So what you can't see in the demo, of course, now is that Joseph is actually feeling a virtual force being applied whenever he comes too close with the remote robot arm to the barrels. So what Joseph is trying to do now is trying to push against the barrels, but he can't because there's this virtual force field. So the robot is preventing Joseph from potentially doing errors, especially while holding materials in the robot's arm. Yeah, thanks, Joseph. That was actually quite nice to see there.
And that's one of the advantages of using this kind of master-follower system, is that you can get inherent haptic feedback and a sense of where the remote robot is, which you couldn't do if you used a purely virtual interface. There is a slight negative in that it can be quite tiring to move the robot around all the time, but I think the advantages kind of outweigh that disadvantage in some ways. Yeah.
And of course, you have other possible additional technological features that you could add. So, for example, because we are using the VR system, you can impose additional information over the radioactive waste. So you could have, for example, the level of radioactivity overimposed as information for the operator, in order to know into which container to sort this the waste. So we have a question from Tanvi here saying, can this virtual reality setup be optimized to operate other machines or robot systems, such as a crane remotely using Wi-Fi? Paul, do you want to answer this one? I'm going to display the question here. Yeah.
Yeah, probably. I mean, so this particular setup, I think, you probably couldn't do that because you can't really do with a master follower system with something large like a crane. But you could do instead use a kind of more of a virtual reality setup where you would have a virtual representation of the robot that you want to move around, and then you can move that around in VR, and that is then represented. Then that movement is then duplicated on the real system, and that then has the advantage in that you can not have the physical tiredness of having to move a real robot around, but also you can use a clutch system, so you can more conveniently position your arm somewhere that it wants to be in order to do the movement. So you could hold the clutch down, move forwards, then release the clutch, move back again, and then move further forward so that you can move beyond where you could normally reach.
Yeah, and then another question from Nayab Ahmed. Can you let us know the camera system being used? Yeah, so that's a Stereolabs Z camera. It's a stereo camera. I think it's one of the few stereo cameras around on the market. So Stereolabs is, I think, as far as I know, one of the few companies who are producing these kind of systems. So maybe to come back to this question from Tanvi, and then I think we have to close. So in general, it's interesting that these kind of systems that we are working on, these kind of teleoperation systems, this is not particular, only for the nuclear industry. So I mean, we find that that many similar systems are, for example, used in minimal invasive surgery. Of course, in that case, you have much smaller movements if you are inserting tools into a human body to do surgery inside of the body. But the principles are very similar. You have the same interaction principles. You have the same teleoperation principles. You have the same principles of having to avoid certain areas, for example, in order to keep the patient who is being operated safe. So we quite often work together with the colleagues from the lab who are working on minimal invasive surgery and medical robotics, because they interestingly have very similar problems to what we are dealing with in the nuclear industry. Okay, many thanks to the team in the room. Thank you, Joseph. Thank you, Alex. Thank you, Mehdi. Thank you, Jennifer, for the live demonstrations. I think that was quite impressive. And we unfortunately have to close at this point. So, hi, thanks, Alex. So, just at the end, let's go back to Paul and me. So yeah, thank you very much to the audience also for the interesting questions, and to your, well, thank you for so many of you being here live to view this. All right, we are going to close now, and I'm going to have to jump over to close the conference together with Arthur.
Thanks a lot.
Yeah, bye-bye.
Bye-bye.